So I'd like to thank the organizers first, Joel, Jifun, and also Avishai and Ari for the workshop. As we move on to the AGORA workshop, my talk is about kinetic SM feedback and other UNLV efforts on AGORA. As I moved from UNLV to Osaka last year, people have moved on to around the world. This talk basically has to be given by Keita Todoroki, who did a master thesis on this topic, but I'm basically giving the talk on behalf of him in some sense. He's now moving to Kansas as a PhD student. Robert Thompson did a lot of work also on AGORA. He's now postdoc at Cape Town after being at Arizona for a year. Juwan Choi is at UT Austin, worked on Graco stuff, which I'll introduce in a few slides. And Jason has worked on cosmological simulations on our part. So I'll go very quickly on motivation because you all had this entire week. I'll show you what we have done on the modeling or why we have to do it. I don't hear me. Oh, here we go. Very strange connection problem.
It's a glitchy, I think.
Yeah, it's a cable problem.
Let me just tie it like this.
Yeah, that'll work.
Let's see.
I'll just hold it, maybe stick it in.
Yeah.
Does this work? Yeah, good. Okay. All right, so to solve these problems, you all know that the feedback is indispensable. It does chemical enrichment, brings the multi-phase nature of ISM, morphologies that we talked about, and then the properties. So we have worked on this, but we have resolution limits in cosmological simulations, and phenomenological models has been developed, as you all know. So people have done different things along this line, turning off the cooling or star formation, or hydro interactions has been sometimes turned off. Notably, the original Springer-Hernquist 03 constant wind model, kinetic feedback, stellar feedback.
That's how it works.
Okay, well, then maybe that's easier. Whichever is fine. I'll just work on this right now. It's still working. So another thing is that as we move more towards the zoom-in simulations, all these models sort of used to use global galactic quantities like the total stellar mass or the velocity dispersion or total star formation rate in galaxies. And that's no longer really viable because we can now resolve these internal structures of galaxies and build a better model based on local physical quantities, and we'd like to do that as well. So we have to update our model as well. We're trying to catch up to people. So this is what the evolutionary phase is. And we looked at, so this is, just let me say that this is Todoroki's master thesis, papers in preparation. So we looked at these SNR evolutionary phases, what you learn in grad school. So you start off with the free expansion phase of about 1,000 years, and then based on these numbers, you get about 10 to 51 ergs of supernovae. And then there's a set-off-Taylor phase where you have 8 APEC expansion, and in this phase, radiative velocity is negligible. And then you go into snowplow phase where radiative cooling becomes important at the outer edges, and then there's a fade away and dissipates into ISM. So now we have better time resolution and mass resolution. We can gradually consider taking these physical processes into account, especially in the zoom-in runs. And then so a drain provides these nice approximations for the shock velocity, shock radius, and the time scales of these phases, for example. So these quantities that can actually be calculated based on the energy available and the densities of the environment. So we do this, and then so now the shock velocity, for example, is smaller for denser environments, or the size of the supernova remnants can be smaller for denser environments, which was all these effects was not in the previous constant wind model, for example. So this, in some sense, it's reducing number of free parameters compared to previous model because we now compute these quantities. So for example, the time scale of these like a end of set of Taylor phase can be computed. It's about 10 to the 5 years on average or so. Fade out time can be 10 to the 6 years, maximum 10 million years. Some people turn off the cooling for too long time. I think we should be a little bit shorter time than 30 million years, for example. So it's a couple of million years would be better to turn off the cooling. We also do gas metal recycling in the spirit of AGORA. Okay, so this is following what we have fleshed out in the flagship paper. Recycling fraction is computed based on the Chabrier like this, and this remnant mass is taken consistently with what we have said in the flagship paper. So this is done along the lines of AGORA initiative. And we also study a little bit about cell feedback, early phases of thermalizing and homogenizing the ambient gas for the 4 million years after the staff formation, before supernova kicks in. Okay, this is similarly done with Stinson's work using gasoline, but we don't turn off the cooling by hand for this period of time. And then we distribute this 10 to 50 ergs per solar massive supernova over 4 million years and deposit it uniformly during this time, and depending on the simulation time steps. So based on this model, here's a summary, quick summary. So staff formation takes place in our model, and then during 4 million years, we let the stellar feedback work. This is a simple thermal feedback in the ceramic medium, which pulverizes them a little bit. And then after this time, the supernova explosion takes place, and then we do the standard kinetic and the thermal feedback using the self-Taylor solution, and then do the returning recycling and such. So, and then during this set of Taylor phase, radiative cooling is inefficient. Therefore, we turn off the cooling for this period of time physically, physical reasoning. So now the time axis is going towards the right to left. This is the same schematic picture, more in detail, conforming to the simulations. So when you form stars right here, star formation, we don't touch it very much for this talk. We are still sticking with the original Springer-Hernquist star formation, or some of the new models we have also. And then so during these 4 million years, stellar feedback works. And then at this point, supernova goes off. We compute the shock radius, and then we know how much influence it has around its location. And we give the velocity kick and thermal energy. Thermal energy 70%, kinetic 30% based on other studies. And then we let the wind particles take off, conserving energy, and then kinetic feedback takes place. Okay. Nothing really especially new, but now we work more physically. That's honestly faithful to the local environment of our high resolution simulations. So we're doing this with Gadget 3 plus our modifications by a group. Maybe, okay. And then all these, the standard thing that we have to include: metal cooling, UV background, star formation. And then one thing that we might want to discuss a little bit tomorrow and Sunday is some of these SPH specific enhancement that has taken place in the last few years. For example, I heard that the field talked about these new efforts on the descent in Bennett SPH. And there are a few additional features that the SPH people boast now, but we have tried a few sets of these as well, and noticed that sometimes the results change dramatically, for example, depending on how you turn on or off the time-dependent artificial viscosities. So I think there's still some things that we have to check when you turn on these new enhancements, and what differences are coming from these new enhancements in SPH. So first, isolated galaxy simulations. This is in the spirit of paper 3 and paper 4 of AGORA. We have been doing this using the exact AGORA initial conditions that have been provided by the collaboration. So this is the initial condition of Milky Way type galaxy, and this is the outcome of it. And we're doing this with 80 PASC and 30 PASC resolution. And these are the parameters for this make disk initial conditions. All these mass and are done with the software length of 80 PASC, okay, standard disk simulation. So here are the sets of runs on star formation history, for example. Okay, so that time runs from left to right. And basically what you want to take from this figure is that if you don't have the feedback, basically you have a large star formation, starburst in the beginning, of course. And then once you implement the original, even the original Springer-Hernquist model, this dotted gray line here, it's this one, without this feedback, and now you turn on the previous constant wind model, this is the dotted line down here, strong suppression of star formation. And likewise, with our new models of supernova feedback, we basically achieve the same thing without invoking these phenomenological models. Basically, so we're doing the same thing with more physically honest way, faithful way. That's what it is. Okay. Stellar feedback doesn't have significant impact. It just slightly decreases the star formation rate compared to the supernova case. Okay. This is a face-on disk image. It has different features. Here's one with the supernova feedback only. Here's a with stellar feedback. And this is only the stellar feedback. The stellar feedback only case, the feedback is not enough. Therefore, they have excessive star formation high density knots in the beginning, and that enhances the star formation quite a bit, and then it produces these pockets of low density regions due to feedback. Okay, so this face-on picture is very different from these two. Okay, in these two cases, they have nice, smooth, extended spiral arms. Phase diagram is another thing that we have to look at in the isolated case. So this will be paper 3-4 issues. Okay, so here's how our phase diagram look like with a supernova only, plus stellar feedback and stellar feedback only. The fraction of the cold gas is quite different according to these feedback models. If you don't have the supernova feedback, you have large fraction of cold gas, which produces lots of star bursts in the knots. And for these two cases, you have more feedback, so therefore the hot gas fraction is slightly higher than this one, although it's much less compared to the cold gas. This is isolated ideal case, so it's not cosmological environment, but you do see this hot gas that is produced from this cold gas. If you look at the movie of the phase diagram, the gas actually jumps up from this cold phase upwards and then goes to 10 to the 5, 10 to the 6 Kelvin area, and then they gradually, if it goes out of the potential disk, it will gradually adiabatically cool, and it goes this way. So this is a signature of the feedback in this isolated galaxy case. Okay, so this is something we can also compare in paper 3, paper 4. Outflow rates, we also computed this. We set basically a plane at fixed height from the disk, like 3 kiloparsec, 5 kiloparsec, and measured how many SPH particle passes through the plane and measured the outflow rates as a function of time. And they do vary quite a bit depending on the models, but we do produce the nice galactic outflow based on this smaller scale set of Taylor-based supernova feedback. Okay, so we're achieving this galactic wind without the constant wind model. So that's the idea. Okay, so now we move on to the tests with cosmological zoom-in simulations. Okay, so things we can address like a stellar to halo mass ratio. So we're doing this using the music code like everybody else is doing. Okay, this is we also follow this AGORA initial condition for this as well. We start from the 60 megapascal Cohen box. This was a low resolution test case with 500 parsecs. And it forms a galactic halo of 10 to 11 solar mass with quiescent merger history at the center of the box. Okay, so we did this, and here's the initial results of this. Produces preferred result. Without the feedback, of course, the stellar mass is very, very high compared to Beruzzi results. And as you add the supernova feedback, you lower it a little bit, and then if you add both supernova 2 and the stellar feedback, you do approach the desired area. And on top of this, if you have additional radiative feedback, Asian feedback, you might even approach towards the right side. So it is a nice trend. But as I said a little earlier, SPH enhancements actually changes even these results too. We actually observed if you turn on, for example, time-dependent artificial viscosity, this results actually sometimes dramatically changes its location. So I think we do want to be a little careful about comparing the results on those details, not just jump onto agreeing observation is always a good thing. And also we observe less substructures after these feedback. So we are actually alleviating the missing satellites problem by this feedback model. So this is the original Springer-Hurquist constant wind model. Whereas this new model, it actually erases some of the small scale structures around the massive halos. So I think it is going in a good direction. Okay. So conclusions, first set. So what we did is basically more physical approach that allows us to do feedback more naturally on a zoom-in scale, smaller scales, reduce the free parameters and artificial adjustments, such as turning off hydro too much. SN2 is good, seems to be good, plus stellar feedback does help, as people have found so far. Without turning off the hydro too long time, SN2 produces the outflows and suppresses self-formation, so that will solve the overcooling problem, and missing satellite problem seems to be also in good direction too. And we are also doing same thing for the dark matter only runs. That was the hydro results, but we have participated papers 1 and 2. So this is from the first flagship paper, and we have been trying to run the higher resolution dark matter cases, and we continue to support the efforts. A few slides on Grackle. In our group, Junwan Choi has been already implemented the Grackle in the old-fashioned way. We're not following the API stuff. We just started as soon as we came up with this, and he already implemented the Grackle in our code. So we're doing this in an old-fashioned way with actually the previous C++ version. Just a few days ago, Jifun sent out emails about the new pure C version released recently. So we're not using this one, but so far it's been fine for us using this C++ version. So basically, Grackle is a chemistry code using cloudy cooling, which also allows non-equilibrium primordial chemistry network. And in our tests, if you turn on the non-equilibrium cooling, it does slow down the code a little bit by about 10% or so, but it's not to the level impossible to run. So I think it's still fine, feasible. So everything seems to be fine so far. Here's how we did it. The details are too technical, but basically you just have a gadget Grackle initialization with C++ wrapper. You basically initialize units, use background models and Grackle parameters. You go to main run, you do the start cooling part in gadget, and during this time you actually go to this wrapper to call the Grackle library. You do the Grackle thing here, and then when you do the cooling, you come back and then get the abundances and follow the standard gadget procedure, and then do the rest of the hydro and body stuff. Okay, go through this. So in order to do this, because we actually started with the original version, we actually have to use the makefile that requires modification for C and C++, which complicated a little bit initially, but it's working. And here's one test that we have done in the cosmological run. So this is a small, like 10 megapascal box, 128 cube run tests. And basically the phase diagram looks okay. This is the original gadget cooling with the Forster-Giguri 2011 tables. And then this side is the gadget cooling using cloudy. So there's some differences. You see these features, for example, here, there's a little bit of a thickness difference, and there's a little bit of shape here. But overall, I think it's reasonably similar, and we can say I think it's working. So this can be sort of like a test bed for other people who are doing the same thing in a different way. Many groups, I heard that already implemented the Nix API to do Grackle implementation. So if you do that, you can do a similar comparison. And if things are consistent with what we find, that'll be an encouraging comparison for us. And we'll also try to do the same to make sure that things are done accurately and correctly. Okay. And I noticed that there are a few observers who discuss about this, so I thought I'll just throw in a few bonus slides for the observer people who enjoyed my talk. So we also, Jason Jakes was a student of mine. He was an undergraduate at UNLV. He produced a lot of good results. He went on to Texas Austin, and he's now working with Steve Finkelstein. And this is one of his master thesis project. And I think it was Eric who talked about this constant number density selection and how the inferred mass growth versus actual mass growth compares. So we actually are using not the zoom-in run, but the full 100 megapascal cosmological simulation as we used to do before. And then we are comparing the growth of galaxies that we find at, for example, redshift 3, and then track them down to z = 0 and see how individual galaxies track the inferred growth of the number density selection. So it seems to follow fairly well with each other. There's a slight difference at the late times, but these orange points are the median points of entire population that you select at z equal 3, follow forward, and then you get this scatter. So this scatter we do see in a cosmological run. Okay, and then how we quantify this scatter and understand it, I think, is the next step. And we also do this to higher redshift. Instead of starting from z equal 3 and going to 0, we also focus on the high z cases. And so we want to fill in the gaps between here, start from like z equal 8, and then bring it down to z equal 3. So Jason is now running, I think, 80 megaparsec or 100 megaparsec, 1024 cube run gadget SPH, and then trying to fill this gap and then bring it down to z equal 3 to compare to observations. So I just want to say that we're doing that also, and then end there. Thank you.
So a general problem with this so-called last wave feedback, as it's been implemented, for example, in gasoline, with a 20 or 40 million year delay.
30 million year delay, yeah.
This is overpressurizing the star-forming region.
Right.
And they never form these gigantic clumps of 10 to the 8 to 10 to the 9 solar masses, which are a ubiquitous feature of observed galaxies that are star-forming in redshifts 1 to 2.
Maybe 30 million years is too long.
Fabio Coronado told me that he has never seen these big clumps in any of his simulations.
Right,
He knows
okay.
that he's overpressurizing.
I see.
And he's going to try to deal with it.
Right, okay.
And I wondered
So,
if by greatly reducing the time scale,
yes.
we're now actually starting to make more realistic.
Right,
galaxies.
I hope so, yes, yes. So, well, that's what we calculated here. So if this is realistic,
Now
I don't know.
What I'm asking is what's the proof of the pudding is to actually see what the galaxies look like.
Right,
Show us a
well,
few examples of
yes.
low redshift. So what
Yes.
if we look at these galaxies at redshifts 1 to 2?
Yes, yes. So that we have to do higher resolution cosmological zooming runs, and we have not done that yet. We only done the low res cases. So Keita is now doing high res zooming cases, and then we can actually look at the morphology at z equal 1 and 2, and really do what you just said, and look at the surface brightness profile and mass density profile, and the velocity rotation curves and such. And that I hope will go into a paper, but we got to press on him a little bit more for the next few months and try to produce that results. But this is a sort of preliminary isolated case so far with this feedback model. Yeah, but yeah, so the result is different depending on what you do on the feedback. So when all the groups come up with different images, as Sandy was pressing on us, what is a measure of success? We have to think about what we're going to compare and what we're doing on the very native level of SPH. What's same and what's not same, and that's the difficult part of the comparison.
I actually have two questions. The first is simple: is there a speed differential in your Grackle versus gadget? Is the Grackle much longer?
No, if you use the table version of the Grackle, it's actually almost same or even slightly faster, the Grackle case. And then if you turn on the non-equilibrium case, it's about 10% overhead for turning on the non-equilibrium. Original gadget table cooling, yeah. So it's not a significant overhead. I think it's a level that we can manage if it's 10%. So.
With your kinetic feedback method, did you play at all with the timescales of the different components? Like you said, 4 mega years was the initial timescale before you actually allowed supernova.
No, we have not played with that parameter yet. But that 4 million years was actually selected from observational papers, so that he looked at some of the supernova remnant papers, and that's seems to be sort of the ballpark of the before it kicks in. So it can't, I think, be too long or too short. So it could be 5, for example, or 3, but we just picked a number between those ranges. So I guess we could play. Of course, like Gavanato's group, of course, if they're using 30 million years, that's their results, and we can try, and if we have time to search the parameter space a little bit more, yeah, that's an experiment we can do.
And for these 4 million years, is a constant energy injection, you said, from?
During that 4 million years, depending on the simulation time step, either you distribute it uniformly during that 4 million years, or if your time step is longer than 4 million years, you just have to dump it right during that time.
And this is sort of 10% of the
Temp-
electric luminosity or something, or how much energy do you put in?
Let's see. So we actually do have one parameter for the stellar feedback. So it's either like a 10%, like 20%, 30%. We actually can pick a number. We're picking 10% right now. Yes.
Any other questions from Chen? If not, let's thank him again.
Thank you.